Okay, we'll start. Well, I'm Hester Jiskoot. I am the chief editor of the IGS, which means the Journal of Glaciology and the Annals of Glaciology. And today we have a special day of the two award winners of the 2024 Graham Cogley Award. So the Graham Cogley Award was established in 2019 in memory of Professor Graham Cogley. Many of you will have known him. He made a substantial and enduring contribution to glaciology, mostly mass balance and kind of worldwide monitoring, but also the White Glacier in Canada, monitoring of that. He also had sustained an outstanding service to the wider glaciological community. He was instrumental in monitoring or mentoring young glaciologists, and he was also the chief editor of the IGS between 2016 and 18 until his kind of premature passing. So this award was initiated after he died, and it was is still generously sponsored by the Cogley family, especially by Graham Cogley's widow, Kathy Cogley, who will be informed of like all the winners, and the winners are encouraged to actually write like a little thank you email to her as well. So the Graham Cogley Award is shared between the IGS and IASC, and it's awarded in the even years to IGS and then the odd years to IASC. And when we do it, we award it to two papers of exceptional quality in either the Journal of Glaciology or the Annals of Glaciology over that past 2 years. So, let's see here. So for this round, there were 116 student authors' papers in the journal and the annals that were eligible. And from those, we shortlisted 15 papers from 7 countries. And from those, we selected the 2 winners that you'll see today. So the nomination and shortlisting is done by the IGS Associate Chief Editors, both of the journal and of the annals. So just so you know, kind of some faces and names. This is the IGS Chief Editors of the Journal of Glaciology at that time. Some 2 have retired by now. And then also there is a number of volumes of the Annals of Glaciology that were had issues and now called collections that were also eligible. So the associate chief editors of those particular ones also selected 1 or 2 of the best papers in their particular issue. So today we have presentations by 2 of the award winners, Tim Hill from SFU and Sarah Wells-Moran from MIT at that time, but now at UChicago. And both of these papers, I'll start with Tim's paper, the improved representation of laminar and turbulent sheet flow in subglacial drainage models. He presented a really novel approach of like a hybrid between laminar and turbulent, where he tested it on a synthetic and on real-time data from Kangerlussuaq, Greenland data from PROMIS. And it's a very extremely thorough testing that he did and very useful results for both modelers and for understanding the subglacial hydrology in general. So it will be very applicable. For Sarah, she actually like wrote this paper when she was still doing her master's, and it is called Fracture Criteria and Tensile Strength for Natural Ice Calibrated from Remote Sensing Observations of Antarctic Ice Shelves. So it was actually a thorough evaluation of 5 fracture criteria. First theoretically, and then like when she like decided on a range of tensile strengths, she actually tested that on the ice shelves in Antarctica. So both these papers, also Sarah's, were very thorough in the theoretical testing and the application to real-time data. So Sarah's results are also predictory, so we can actually apply it for both ice sheets and ice shelves. I must say it's just for surface strength and surface crevasses, not for bottom crevasses. So both of these papers are exceptional in the depth of analysis, the quality of presentation, and the overall potential impact. And both of these speakers today will actually present the extrapolation of that work. So they've done a lot of new work since they actually submitted that. So what do these Graham Cogley Award winners receive? They receive certificates, award money, 500 Canadian. They're recorded in the IGS Awards recipient list. They present here at the IGS Global Seminaries and Seminar Series. And all shortlisted papers form a special collection in the Journal of Glaciology. So you can actually find these all bundled together. We now have that done for 3 years. And these shortlisted papers also include the other 13 shortlisted papers. And I'll just quickly mention the names. Nicole Abib, Anna Brown, Eddie Feathers, Emily Feathers, Nicolas Gonzalez Santa Cruz, Aris Hansche, Elliot Jaeger, Benoit Lauzon, Brittany Main, Francis Meloche, Lilian Schuster, Joram Terlet, Maximilian van Wijk de Vries, and Jessica Voveris. So all these papers were exceptional and were selected out of the 116 eligible papers, and about 5 of these are from the Annals, and the rest is from the Journal of Glaciology. So I will leave you with a selection of some of the good graphs in some of these papers, and I invite you to actually read them all and to actually listen to. First, we have Megan presenting, and then we have Tim presenting, and I'd like to congratulate both of you and have a round of applause from us for the award winners. So I'll stop sharing.
All right, I think I am up next. And doing the standard Zoom question. Can everyone see my screen?
Looks good. Go ahead.
Awesome. So thank you so much for the introduction and for the opportunity to give a talk in this seminar. This was my first project I ever did in glaciology, and so it's really fun to have it recognized in such an awesome way. So kind of a little bit about me. I started this research when I was an undergrad at Wellesley College, and then kind of continued working on it, finished it up during my master's at MIT, and now I'm a first-year PhD student at University of Chicago. If you hear any screaming in my background, that is my cat. She's bribed with a heating pad right now, but to be determined how long that lasts. Um, and very big thanks to Brent Minshew and Meghna Ranganathan for their support during this project. Brent was my advisor at MIT, and Meghna's my advisor at UChicago. So to kind of get into the meat of the research, the motivating question for this work is, what is the tensile strength of ice? And historical estimates of this value have this massive range. Observationally, the tensile strength has been estimated to be between 76 kilopascals to 1 megapascal, so huge range, and lab estimates also order of magnitude range from 500 kilopascals to 5 megapascals. And another important question is, why does tensile strength matter? And it matters because of the models we use. A lot of large-scale ice models use calving and damage as one of the methods that ice mass is lost. And a lot of models have this kind of critical stress threshold that they use to simulate when damage will occur or when a calving event will occur. And a lot of models use ranges from 100 kilopascals to 1 megapascal. So again, very large range. This introduces a lot of uncertainty into these models. So for our approach, we wanted to see if we could distinguish stress states associated with active crevasses from general stress states in ice. And this paper largely follows the methodology of David Vaughan's 1993 paper. You can see a figure from that paper on the right. And David Vaughan did this entirely with field measurements, and we leveraged having satellites now and have vastly more data points, so can kind of constrain this range a lot further. So to kind of go briefly over the methods, first step was to identify fractures. Then from the fractures, we inferred stresses from observed strain rates, and then we drew yield criteria around the inferred stresses to try and delineate between stresses present in crevassed versus uncrevassed ice. For identifying fractures, one of the main challenges is that a lot of fractures that are visible on optical imagery are inactive crevasses. And so in order to filter for this, we filtered out inactive crevasses by looking for crevasses that were visible on both optical and on strain rate fields. These fields are all from 2014. So as an example of active crevasses, this box right here shows a region on the Ross ice shelf where the rifts are visible very clearly on the strain rate imagery and also on satellite imagery. And then here is another example, just adjacent to those fractures on the Ross ice shelf, where there's a lot of crevasses that are visible, but there's no evidence of them in the strain rate field. So these crevasses may have formed upstream and then advected downstream into stress states that aren't associated with formation. So we just wanted to make sure that we were looking specifically for active crevasses to try and really get that clear delineation. So after we go in and infer stress states, we tested for both n equals 3 and n equals 4 in this situation. Next step is to look at the yield criteria. So yield criteria are bounds defined by material properties that delineate stresses past which failure should occur. And in this situation, we're describing failure as creating a new surface. We're not really distinguishing between brittle and ductile failure. So what this looks like, we have this little parcel of ice, and if we measure the stress states the parcel of ice is under, say put it in that region, that bit of ice is intact. It is within the bounds of the yield criteria. Now say another parcel of ice is in a region that's outside the bounds. That means that there should be crevasses there. And so when we plot stresses of ice into this principal stress space, we can look and see where they fall and see if we can draw these yield criteria around them to accurately delineate where the ice is not crevassed and where crevasses exist. So we use 4 yield criteria, and these criteria are based on certain material properties. The size of the criteria is determined by certain tuning parameters, which are in parentheses next to them. These are the cohesion and internal friction for Mohr-Coulomb and Drucker-Praeger, and then just the tensile strength for von Mises and Hayhurst. What's really cool, in my opinion, is that these criteria all kind of like build off of each other in a way. So for Mohr-Coulomb was originally designed for shear failure, and that's one of the long-standing yield criteria that's used by a lot of fracture mechanics people historically. Von Mises is based on the octahedral shear stress. Drucker-Praeger just tacks on an extra term to von Mises that's based on pressure. And then Hayhurst tacks on an extra term to Drucker-Praeger that depends on maximum principal stress. And Hayhurst is particularly interesting because it's used in a lot of continuum damage mechanics models, so could potentially be applicable to a lot of future modeling efforts. And a last point is in David Vaughan's paper, he plotted everything in Cauchy stress space. The challenge with yield criteria is that they are all defined in terms of Cauchy stresses, but the way that we infer stresses from velocity data, all of the stresses come out in terms of deviatoric stresses, and so you can't just like plop one on top of the other. So we, instead of converting the inferred stresses into Cauchy stress space, we instead converted the yield criteria into deviatoric stress space. And so they look like this in deviatoric stress space. So if you're familiar with yield criteria at all, they might look a little bit different. It's that conversion that causes the different shape. So here are our results for tensile stress. So if you see here, these blue points are all areas that are not crevassed. The red are all areas that are crevassed. And this color scale tells you kind of the density of points in that area. And then these lines here are all of our best fit yield criteria. You can kind of see there's a decent separation between the areas that are crevassed and the areas that are uncrevassed. And we kind of change the tuning parameters to change the size of the yield criteria and calculate how many points are in versus out of the criteria. Our results for n equals 3 are tensile stresses between 200 and 260 kPa, which is within the range that David Vaughan predicted. And then for n equals 4, we see higher yield stresses of 420 to 565 kPa. And just as kind of like an intuitive method, because principal stress space was very confusing for me to figure out at first, these colors in the background plot to these colors on this graph right here. So anywhere in blue here is in tension, anywhere in gray is in a mixed regime where one principal stress is positive, one is negative, and then red is a compressive regime. And another important observation is that there are no crevasses that we observed in a compressive regime, which makes sense because the majority of these ice shelves are tensile. All of these criteria fit pretty well in the pure tensile regime. Starts to get a little bit dicey in this kind of mixed regime. Here it kind of appears that von Mises fits the best because it kind of has the fewest included in this region. And so then we kind of decided to see what would happen if we applied these yield stresses to all of Antarctica. So this is kind of what that looks like. And the kind of thinking behind this is, can we use these results to predict fracture? So these maps are really good at catching large-scale fractures, but they're not as able to resolve smaller features. What's really interesting is, so this gray area right here shows that 3 criteria say that this shouldn't be fractured, and 1 criteria says that it should be fractured. And the 1 criteria here is the von Mises criterion. And so that the von Mises criterion kind of predicts or over-predicts fracture in these shear regions. We can see there's some areas that all of them are predicting fracture, but there isn't fracturing observed. And kind of unclear as to why that might be. This region on Amory is quite interesting because these linear features here are all fractures that are observable on optical imagery. They also show up in the strain rate fields. We just didn't include them because of their proximity to the shear margin, but this map does accurately capture all of those. And then this is the fracture that formed the A68 iceberg and very clearly picks up on that. So good for predicting large-scale features, less good for predicting small-scale. Then we decided to take this to smaller glaciers that they were not included in our original search for crevasses. Again, kind of hard to pick up the fractures that are they're smaller relative to the spatial resolution, but it is really good at picking up areas that are kind of visibly damaged. So, for example, this is the Thwaites Eastern Ice Tongue in 2014 before it kind of really shattered. And all of these criteria are kind of predicting that it should be relatively fractured, whereas the Western ice shelf still relatively intact here. Again, there's like this is Totten ice shelf. There's a lot of damage here. That's all picked up there. Pine Island is a bit of a special case because all of the criteria think that this should just be incredibly fractured. And it's not really visibly fractured in 2014. So it kind of breaks down in areas of fast flow. And then what's also really interesting is von Mises is the only criteria that predicts fracturing in a compressive regime where there are fractures actually observed. which is right by the McDonald ice rumples on the Brunt ice shelf, which is outlined in yellow here. So quite interesting that von Mises is the only criterion that's able to pick up those compressive fractures. So to revisit our motivating question, why do we care about tensile strength? And the answer for that is, again, calving models. And the goal of this work wasn't to kind of say, this is the tensile strength device, this is the criteria we should use. It was more to provide this giant range that modelers can pick and choose from to find what best fits their particular situation. There is no best model based on our current understanding of ice fracture and all of the uncertainties that go into these calculations. And as we saw with the predicted fracture map, some criteria work better than others in certain regions like shear margins versus in the center of the ice shelf. So we are hoping to just provide a grab bag of numbers, and there are lots of tables of numbers in this paper if you would like to grab them and throw them into your models. So this full range over here is kind of what we predicted for n equals 3 in purple and n equals 4 in blue. It is worth it to note that the low range estimates of tensile strength are likely not to be the most accurate because of the previously mentioned crevasse advection. These were defined, the low estimate was defined by no crevasse points included in the yield criteria. And so if some of the crevasse points still had managed to advect downstream, out of the stress state of formation, the low estimate is not likely to be as representative of stress states. And that shows in that the kind of best fit estimate and the high estimates are close to each other in every single case. So some implications, n equals 3 versus n equals 4. What's really interesting is that the predicted values of tensile strength for n equals 4 are within the low end of laboratory estimates. When I was kind of starting out in the field, I was reading a lot of papers, a lot of textbooks, and a lot of them were very skeptical about whether or not lab estimates could be applied to natural settings. I've taken this screenshot of Cuffey and Patterson where it says, like, laboratory experiments don't achieve the high strain values expected in dynamically important zones of glaciers, and thus results of laboratory experiments should not be applied to problems in nature without field evaluation and calibration. And this kind of 250 kilopascal discrepancy between observations of tensile strength when n equals 3 and lab estimates of tensile strength has previously kind of been explained with, oh, damage in natural glacier ice or other like discrepancies between lab environment and actual ice. But with these n equals 4 estimates, I think it brings us a lot closer to reconciling this previous massive gap in lab estimates versus in field observations. So I am a little biased towards the n equals 4 side, but I think it's pretty cool that our n equals 4 estimates for tensile strength are like pretty close to that low end of lab estimates. Another thing is looking at compressive strength of ice. 3 out of the 4 criteria we tested allowed us to also have predictions for compressive strength. Now, given that we didn't observe any fractures in the compressive regime, it's kind of impossible to say whether or not these predictions are actually accurate, but it is kind of interesting to look at how specifically the value of internal friction impacts compressive strength of ice. In a lot of ice models, it's been set to pretty low values, which for the criteria we tested implies that the tensile and compressive strengths are very similar, if not the same, which is not often observed in nature. Usually the compressive strength is much larger than the tensile strength. Also, as Hester noted in the beginning, this is only for surface crevasses. We're not able to resolve basal crevasses or tensile strength at depth. Last interesting point is that tensile strength estimates are pretty close to the inferred stresses that govern ice flow. So if you go out and calculate stresses on an ice shelf using n equals 4 or n equals 3, all of the stresses that you find are like within 50 to 100 kilopascals of the tensile strength estimate. So this potentially implies that there are similar processes involved in ice flow versus ice fracture, and potentially like dislocation, tangles, or pileups could be involved in fracturing. So that could be a very interesting mode to pursue in the future. My current work, I just submitted a paper last night, so it was up quite late about Pine Island Glacier and its shear margins, and I'm currently very interested in ice shelf stability, damage development and evolution, and looking at shear margins. So thank you very much for your time and attention, and happy to take questions, or I don't know if we want to do questions at the end.
Amazing. Great. Thanks, Sarah. Yeah, we'll take some time for questions for you right now before jumping over to Tim. So, thanks again. That was excellent. Do we have any questions? Yeah, Michael.
Sarah, this was an amazing talk and paper. Thank you so much for sharing this. Maybe I missed it, but what velocity data sets are you using for your strain rates? And have you like kind of done some sensitivity among different velocity products and like sensor types to see how much the your criteria changes based off of what velocity you input?
Yeah, so we were using Landsat 8 derived surface velocity from Gardner et al., but didn't test between various velocities. So that could be a very interesting um, like future direction. Another thing that I was thinking about in preparing this presentation is like this is all 2014 data, and potentially looking at like Sentinel-1 derived velocities on like specific ice shelves and specific areas could kind of suss out some of these uncertainties in like having, I don't know, just the one time frame. This was kind of more of like a broad all of Antarctica assessment of fractures, but we also had 36 total fractures that we were able to identify on both strain rate and optical imagery. So could definitely use another person kind of going through and doing this in like specific areas, especially.
Awesome. Thank you.
Great. Anyone else? Questions for Sarah? Okay. I think we'll leave it there. Thanks very much, Sarah. That was excellent. And congratulations again on the excellent paper and the award.
Thank you.
And with that, we'll move over, sorry, to our second speaker, Tim Hill, who is joining us from Simon Fraser University here in Canada. And Tim was also the other recipient of the Graham Cogley Award and will be presenting on his work. And once again, just save your questions until the end, and then we'll ask Tim at the end of the seminar. Thanks very much, Tim.
Great. Yeah, thanks so much, David, Alan, and Michael for setting this up. This is great to have Sarah and I have the chance to talk about this, so thanks. So yeah, I'm talking about two of my PhD projects, and it's actually the first project and the last project of my PhD. So this is kind of a unique opportunity in that way. And the themes are going to be subglacial drainage modeling, but going all the way from the in-detail physics of the models, which, as Hester said, is what our paper was recognized for, and now going up to how can we scale up these subglacial drainage models to things like continental scale in a more efficient way. So the physics that I'm interested in sort of relates to two of the limitations that I see in the model outputs that I run. So I'm going to be talking about the glacier drainage system model, or GLADS. And here's an example of the flotation fraction, or water pressure relative to ice overburden, for something representative of the Western Greenland ice sheet. And first, what I see is that the winter water pressure here is about 30% of overburden. What we'd really like is to just push that value up to something a lot higher, like 80% of overburden or more. That's what you see in things like borehole water pressure time series. The other thing I see with this curve is that my water pressures are very high when surface melt first really reaches the bed in this pulse here. I mean, water pressures are above 150% of overburden, and this lasts for 20 or 30 days. So that's a little bit non-physical because, of course, you'd have some uplift of the ice, which increases drainage capacity and lets that water be drained. So with those kind of in mind, The physics that we hypothesized might address at least one or two of these is the way that water flow is parameterized in the subglacial drainage system. And I'm going to start with this diagram on the left called a Moody diagram. And this is a classical hydrologic diagram, and the curves on it come from experiments of flow through smooth and rough pipes. The x-axis of the diagram is the Reynolds number, which is a non-dimensional indicator of laminar or turbulent flow. Just means we have laminar flow on the left and turbulent flow on the right. And the y-axis is the Darcy friction factor, which relates the pressure drop to the flow rate. And what these experiments show is two totally distinct regimes. You have one laminar regime on the left, some sort of transition, and then a very distinct turbulent regime at higher Reynolds numbers. But what does the subglacial drainage model do? So it has this other parameterization for Q here, which looks different than the Darcy flow law, but it can be cast in quite a Darcy-like way. And in fact, depending on these free exponents, alpha or beta, you can get either turbulent flow or laminar flow, great. But one of the challenges is this has to apply across the entire range of Reynolds numbers. So you're not going to have something that's always self-consistent. I also want to point out that what's sometimes used in the literature is a smaller value for alpha that gives you a positive slope. It's not supported by the pipe flow data, but there's also, of course, such a difference between lab experiments through pipes and the actual subglacial drainage system. But anyways, what I would really like is something that transitions from laminar flow to something like turbulent flow at appropriate Reynolds numbers, and maybe having a smooth transition is going to be useful for numerics or something. And our idea of how to accomplish this is to rewrite actually how we write this conductivity K and take away this choice you have to make on the exponents alpha and beta. So as I said, the way that we do this is adjusting the conductivity, and we really just add a factor that depends on the Reynolds number, so that in some ways you can think of the flow parameterization as being self-aware of whether flow is laminar or turbulent. And this turns out to be algebraic, you can solve it, so it's really easy to do numerically. This is the exact same form as what the Shakti model uses for subglacial hydrology, but there it's interpreted as switching between inefficient and efficient drainage elements, whereas for us it's always the distributed drainage system, but transitioning from laminar to turbulent flow. We do a bit of a slight modification, and we actually rewrite back in this free parameter alpha. That's because, as I said, there was kind of the two options for turbulent flow, so we just want to have that flexibility in this parameterization for now. And now that was enough math derivation, so I'm going to compare the models and then talk about how we implement them. So to visualize the different parameterizations, I have this log-log plot that's the flux Q versus the sheet thickness H. Of course, turbulent and laminar models just plot as straight lines because it's log-log. And the transition models, which I'll be plotting in these shades of yellow, do what we hoped. In the laminar regime, which is the lower left of this plot, they have the same slopes the laminar model, meaning flow is laminar. As the sheet thickness and flux increases, you get more vigorous flow, the flow transitions to turbulent, and the slopes of the yellow transition lines bends over to match the appropriate turbulent models, depending again on this turbulent flow exponent. So to actually test what this does to the model drainage system, we implement this in the glacier drainage system model. I use a synthetic ice sheet margin setup, intending to represent sort of part of the land terminating Greenland ice sheet. We force it with air temperatures from the lower K transect weather station, hoping that we get sort of the right temporal variability of surface melt, because that's really important for driving subglacial drainage development and variations. And I have 68 moulins on the surface and accumulate melt within those to provide localized inputs to the bed. And now we can look at what this does to the drainage system. So there's going to be these 5 models, which is a lot to look at. This is the model drainage system in early summer, July 9th. The purple colors show flotation fraction, again, like the percentage of overburden. And the brown branching features show the discharge through subglacial channels. The main difference between all these models at this point in the season is actually in the upper part of the domain above where surface melt has reached so far, where we just have higher water pressure, darker colors for the transition and laminar models. Below about 30 kilometers or so, where there's subglacial channels, there's not much difference between the models because I haven't changed the channel parameterization. All 5 of these panels have the exact same flow law for channels. So of course the drainage system is the same where it's dominated by channels. What is maybe more interesting is looking at seasonal variations in water pressure for these different models. So I'm extracting the time series of flotation fraction at that same 30-kilometer mark, and I can add back on the air temperatures just for a bit of context. In the early part of the year, from sort of May to June, surface melt hasn't reached this 30-kilometer position yet, which means we have the winter drainage system. And what we see is much higher winter water pressures for the laminar and transition models. That's these dashed and yellow lines at about 70% of overburden. That's great. That's one of the things that I talked about. The other motivation maybe didn't really get much better. So we still have high water pressures, 150% of overburden lasting for quite a while. And in fact, this transition model, which is the one I'm proposing is physically consistent, has about the same summer water pressure as the turbulent model. In the main part of the summer, from July to September, this part of the bed at 30 kilometers from the terminus becomes quite channelized. So as I said, the models all have the same channel behavior. But what is interesting here is to trace across what the winter water pressure was, which is this dashed line. And you can see now we are getting these summer water pressure minimums for the laminar and transition models. And this is one of the classic ways that, one of the classifications for Greenland ice sheet outlet behaviors. And it's one that traditionally has been pretty hard to recreate using GLAD. We were excited to see that. And as I mentioned, we still have the elevated summer water pressures with the turbulent models. So as the last kind of result for this, I want to return to this Moody diagram that I started with. And we can actually put on top of this what the model predicts for the friction factor and Reynolds number. For the turbulent models, partly because of the Reynolds number range that we just happened to get, they're not really consistent with the experimental data, but again, lots of difference between lab experiments and the actual drainage system. The laminar model is closer, maybe, but at this upper Reynolds number range of about 10 to the 4, it is really underestimating the flow resistance. And the transition models do what I said, and they transition from laminar to turbulent flow. If we had higher Reynolds numbers, it would be more dramatic, but still, they are the only ones here that are totally self-consistent. So this was published in the Journal of Glaciology 2 or 3 years ago. You can find the QR code if you're curious. And I want to point out that since this was published, we've implemented this parameterization in the version of GLADS that's inside the ISSM ice sheet model. So if you're doing ISSM ice sheet modeling and want to run the hydrology part with GLADS, you can play around with this parameterization and maybe it helps improve your seasonal water pressure variations. Okay, and then as I promised, part 2 of this is sort of what's happened since that paper came out. And this is looking at machine learning or statistical emulation. So when I ran the glacier drainage system model to make those figures from the last project, I had to assign values for all of these parameters in this table. This is probably familiar to most modelers. There's always tons of parameters you need to set. One challenge with GLADS is your simulations can take sort of hours to weeks depending on your resolution and the size of your catchment and all of that. And this makes it hard to address uncertainty in these parameters since many of the ways to address uncertainty require a large number of simulations and maybe even sequential simulations. So our idea is to bypass the expensive step using an emulator, which for me is just any fast statistical model that approximates the physics-based model GLADS. It gives you almost the same answer as GLADS. It's a really good approximation, but it takes something like seconds or less to make a prediction instead of hours to weeks. There is going to be some sort of upfront investment in model training, but hopefully that's one time. So hopefully this does let you do some analyses that would be hard using the model directly. And what kind of applications might you want to be able to do with this? Two sort of classifications that I've thought about lately is the first is you can actually replace the physics-based model in any workflow that requires sequential sampling. So if I'm going to try to estimate GLAD's parameters from some data, I might have to run a first guess of parameters, do some sort of gradient descent algorithm. That gets expensive because you have to run the model sequentially. Each model run depends on the previous. And that's the same thing sort of for Bayesian inference and model parameters. And as a very brief example, I want to talk about something we've tried to do, which is calibrating the model parameters using a time series of borehole water pressure. So if, for example, I think that there's uncertainty in many model parameters, I can actually just sample from that uncertainty and run some sort of ensemble based on that. And that's what I get here in gray. So this is for a different Greenland ice sheet outlet glacier, but the units are the same. It's flotation fraction. And in gray, I have huge uncertainty at first. I have water pressure ranging between 50 to 100% of overburden in winter. But then if I have some data, which I've put in blue here, I can calibrate my parameters based on that data or condition on that data and get a better fitting model with reduced uncertainty. So in red, the calibrated model closely fits the data and has much reduced uncertainty. There's still a huge spread in this kind of spring pressure wave, but for the rest of the year, the uncertainty is reduced from maybe 50% of overburden to maybe 10% of overburden, which is really good. And this is accomplished by reducing uncertainty in parameters, and you can learn what values for 8 different model parameters best fit the data. And if you want to hear more, because I know that was super short, we have a paper in the Annals of Glaciology recently about this. But what I really want to focus on for this is the newer stuff, which is thinking about these kinds of emulators as a parameterization of a physical process within some other complex model. So this is really popular in climate modeling right now. So there you have this 3-dimensional grid that covers the entire Earth's surface. And say in the atmosphere grid cells, you have these convective processes in this box on the right happening at really, really small length scales. You have no hope of resolving these processes using your actual global climate model that has to run for hundreds of years. So you have to parameterize them, and that's not new. But what is happening a lot now is you can use some sort of machine learning model to parameterize these, train that based on a combination of data and high resolution process model simulations, and stuff that back inside your large climate model. It's a bit different in glaciology, but I'm going to view subglacial hydrology as a parameterization within an ice sheet model. So in that kind of perspective, thinking about hydrology as a parameterization, I think it needs to be spatially transferable. And here, as you can see, I'm moving to Antarctica because when we don't have the surface melt dimension, things are a little bit simpler in some ways. So by spatially transferable, I mean if I maybe don't have training data for the whole ice sheet, I still want to be able to predict where I don't have training data. I want to be able to have the ice sheet geometry evolve because, as we know, grounding lines are going to be retreating. The ice sheet's going to be thinning near the grounding line. I want the parameterization to still work when the ice sheet has changed because retraining means running GLADs again, which gets very expensive. And I still want to include this parametric uncertainty quantification piece, which essentially is those envelopes I had on the last slide around my mean simulations. And our idea of how to do this is we can do a limited number of GLADS runs that cover a lot, but not the whole continent. So this so far has been 7 ice flow basins here. The ones with effective pressure, these are where we've run GLADS. And I, again, am actually running a 100 perturbed parameter simulation ensemble for each of these. And the idea is essentially fill in all of these gray areas where I don't have GLADS runs using some sort of statistical model. The very similar thing has been done by Verjans and Roble for Greenland using a convolutional neural network. So I'm thinking about this as a regression problem, where I have some sort of features or regressors that I think are going to be important, and then I use my domain expertise to identify those, and I try to find a relationship between those values and my simulated effective pressure using the GLADS model. And what I think might be important are basically all the model geometry enforcing fields. So I've sort of put everything in here. I have for the Amundsen Sea Basin here, just as a sort of illustration, the bed elevation, ice thickness, and surface elevation might all be important. The distance to the grounding line as sort of an index of how coastal it is, or maybe an index of how much the marine boundary condition is going to impact the model. The basal melt rate, since that's the driver of the subglacial drainage model. The Shreve potential, which is when you assume water pressure is equal to overburden, and then the slopes of the geometric factors. So as I said, sort of everything that goes into the subglacial drainage model. And I try to do actually a pointwise regression between those things and effective pressure, and I parameterize that using something called a random forest. It's grid cell by grid cell, meaning it takes these 9 values for every grid cell and tries to map those to the modeled effective pressure value. We like using the random forest because it's a very simple statistical model, meaning it has only a few parameters that need to be fit compared to something like a convolutional neural network, even though a CNN might be a more natural choice because it actually includes this neighbor information. For us, we totally discard the neighbor information and just do it in a pointwise way. But regardless, it seems to work, and we like that it's really fast. It takes less than a minute to train this model, so it makes it easy to explore a lot of questions about the model. And right away, I can train that model and get things that are pretty exciting. Like I can predict continental scale effective pressure fields like this one in just 4 seconds. So this is with the random forest at 2 kilometer resolution. And something like this would take, I would say, well over a week using GLADS directly. And that's on many CPUs in parallel. And that 4-second prediction is just on one CPU with also very little memory requirement. So it is indeed fast, and if we trust it, would let us scale up what we can do with subglacial drainage modeling. But the key is actually in assessing whether or not we trust the model. So I do what I'm calling a cross-validation exercise to see how good this random forest parameterization is. And my only metric for good is whether it looks like the GLADS model, since we don't have enough data to assess it based on data. So by cross-validation, I mean I have 7 total basins, but I actually retrain the model on 6 and hold the 7th one out as an independent comparison against the physics-based model. And my overall R squared when I do that is 0.65, which maybe leaves some room for improvement. And I have written around the comment here what the R squared is for each of these basins since I repeat that exercise 7 times. So it's maybe a crude estimate of basin scale effective pressure. But if we just kind of keep pushing forward and do the next step, which is using this to model ice velocities, the picture gets a little bit more interesting. So when we drive an ice flow model, the ISSM ice flow model, using these 2 different effective pressure fields, the GLADS field and the random forest, then we actually have an R squared of 0.99 between those speed fields. So maybe it actually is okay for ice flow modeling because, for example, maybe some of the errors are at length scales shorter than what ice flow is sensitive to. But this is still a little bit challenging because this is still in present day and everything is constrained at present day by our friction inversion, so everything looks like present day surface velocity. So what we want to do is see what happens in the future. So instead of running transient simulations for 100 or 300 years, which is really expensive, I just take snapshots of plausible ice sheet states at 2050 and 2300. So I take a thickness change from a certain ISMIP model projection, and the thickness change of 2300 is shown in this figure. And for this future geometry, I solve the basin scale stress balance. I use a friction coefficient, which is stable in time. So I infer it from present day conditions, carry that friction coefficient into the future. And I solve the forward velocity problem with 3 different effective pressures using the GLADS model, right? So that's the reference, using this parameterization that I've put together, and also using the perfect ocean connection model, which I would say is maybe the most common for these types of ISMIP projections that I'm drawing a thickness change from. And then for those 3, I do a subset where actually I freeze the effective pressure in time, which essentially reverts us to a Weirtman sliding, and that's just kind of useful context. So there's a lot you can look at here because we have so many basins, but I'm going to focus on Thwaites, right, since we know a lot about Thwaites and it's very interesting. And for Thwaites, I've done the projection at 2050. And here we're looking at the surface speed flowing from left to right for the 100 kilometers nearest the present day grounding line. And what I first see in these speed curves is that there's two groups. The top group, which has the darker lines, these 3 darker lines, are where effective pressure changes with ice thickness, which I mean is what you would actually do when you're running a subglacial drainage model. But what we find in the lighter group on the bottom is that we get slower speeds if we don't let effective pressure change in time. So in some ways, this is verifying what we know, which is that having active subglacial hydrology or some sort of ice hydrology coupling is important because you get faster flow speeds by doing that. What is maybe interesting to point out is that across the different basins we have, this difference in grounding line speed is up to 2,000 meters per year. So it can be very sensitive to how you parameterize effective pressure. In terms of the random forest, I can say that GLADS is, of course, our reference. That's the purple curve. But then if we use the random forest, we get, for Thwaites, maybe a couple 100 meter per year difference in grounding line speed. But we've taken our computation time from 5 days to run the GLADS model to half a second to predict with the random forest. So to me, that's a pretty good trade-off. We can also add on here the uncertainties associated with my perturbed parameter ensemble. So here, these vertical bars represent the 1 and 2 sigma spread when I sample from a wide range of GLADS parameter values. And the square markers are just copies of what the grounding line speed is for all the curves for reference, because it's easier to look at that way. What I find is that GLADS, by tuning parameter values, you can either make it as sensitive to changes in ice thickness as the perfect ocean connection model, which in most cases overestimates the speed up, or you can make it as weakly sensitive as effective pressure just not changing in time. So while sort of we have an estimate, maybe one estimate here in the figure of what I think the impact of hydrology is, it's actually still quite uncertain. There's a more complication here, which is that since we have a basal friction step in between running the hydrology and dynamics model, that the sensitivity to effective pressure is actually backwards. I get the fastest speed, so the upper end of these intervals is simulations that have the highest effective pressure. And simulations with the slowest speed are the ones with the lowest effective pressure. So this kind of makes it challenging to say quantify how hydrology would impact dynamics without doing the coupled modeling. And I think this random forest is a really good way to approach that because we can take computation times from 5 days to about half a second. So I've probably gone a little bit over the time that I was supposed to talk for, but I'll just leave you with these kind of 3 graphical summaries of what we've done. I'll point out there's QR codes for the first 2 projects if you are interested, and watch out for a preprint coming pretty soon about this Antarctica project. Thank you.
Great. Thanks, Tim. That was excellent.